What's going on, guys? So today we're going to be going over a few hydrostatic problems. Now, before we actually get into the example problems, I just want to make sure that we have notation, covered. You could definitely skip this part of the video straight to the example problems. But first things I wanted to go over are the different pressures we'll be seeing. We will be seeing PABS. This is the symbol for absolute pressure. PG is just to say gauge pressure, and then PATM is going to be our atmospheric pressure. Now, basically, absolute pressure is the pressure measured with absolute zero as the reference. PG is going to be the difference between absolute pressure and atmospheric pressure. And important thing to know, if your system is not sealed or it's exposed to atmospheric pressure, then the gauge pressure is going to be zero. So first example, we're going to have this pressurized box, and it's going to have a gauge meter. Right here, gauge pressure meter. And our atmospheric pressure is just going to be 1 atm. We're going to keep this problem really simple. So our meter is telling us that the gauge pressure is 0.36 atm. What is our absolute pressure? So this is really simple. All we have to do is we just have to know PABS is equal to P atm plus PG. So our absolute pressure is literally 1 plus 0 to 0.36. So our absolute pressure in our pressurized vessel is going to be 1.36 atm. So it's kind of important because it gives you a kind of a comparison between the atmospheric pressure. You can see now that this is 1.36. It's definitely pressurized over the atmospheric, which is 1 atm. I know if this sounds like common sense, but it's a pretty important concept to know. If we have a vacuum, and our vacuum meter is reading 36 kPa, and our atmospheric pressure is 92 kPa, then our gauge pressure is actually going to be negative 36 kPa. Because this is a vacuum, so the gauge pressure is just going to be negative. So now to find the absolute value, it's going to be atmospheric pressure minus our gauge pressure, which ends up being PABS is equal to 0.55 atm. Cool. So now let's start talking about hydrostatic pressure. Now we have three different tanks. Points 1, 2, and 3 are at the same height. Point 4 is not. Now, how would we rank these in magnitude of increasing pressure? So if we know that point 1, 2, and 3 are the same height, then we have to know that pressure 1 is equal to pressure 2 and it's equal to pressure 3. Pressure 4 has a higher depth than these guys, so pressure 4 will have the highest pressure. Now let me basically explain this. You have to think of pressure as a cross-sectional plane, an infinite cross-sectional plane, right? So this dot is just right in the middle of this plane. This dot is also in the same plane. This dot is also in the same plane. So fourth dot is not in our plane, right? It's in a lower pressure plane. This is just a visual way to seeing it. Now the mathematical way of explaining it is we're going to go and introduce you to the hydrostatic pressure equation. So that means P is equal to rho GH. Rho is our density of whatever liquid we're dealing with. So let's say this is water. Our density will be 1,000 kilograms per meters cubed. That's just the density of water. And this is going to be our gravity term, negative 9.8 meters per second squared. And this is going to be our height. Now we can start explaining why 4 has a higher pressure than 3, 2, and 1. So if we were to quickly calculate this, another thing too is that something I forgot to explain is that you set your surface whenever you're dealing with liquids in a tank, right? Hydrostatic liquids. You set kind of a datum plane or datum line. That just basically means you're setting your reference, and so this is going to be starting off at 0. What happens is when you're dealing with hydrostatics, if you ever go down, you're actually adding most of the time. So you're adding, and when you're going up, you're subtracting. So in this case, it's kind of, say our axis is normally our axis. We're used to writing it like this is positive x and this is positive z. Hydrostatic problems are positive c. Positive z is actually going down, while the x stays the same. So if we go up, this is going to be our negative z. So now, if this is our reference point right here, where this is z is equal to 0, then this point will be z is equal to height, right? Because you're basically just measuring down from your reference point. So this is going to be some height. Height 1, we'll call it. Well, point 2 has that same reference, so this will be height 1 as well. And then the same point you measured will also be height 1. Point 4 is located in a height 2. Height 2, in this case, is going to be greater than height 1. So just putting in, let's say height 1 is 1 meter, and then height 2 is 2 meters, right? Our densities, if we're assuming it's in the same liquid, these tanks are filled with water, then our densities are going to be the same. Gravity is always the same unless you leave our planet. And our height, the only difference is that point 1, 2, and 3 are going to be rho g, 1, and then our point 4, for point 4, is going to be rho g, 2. Now I know I'm sorry if I oversimplified this, but it's really important to know this. So now let's calculate the pressure. Let's calculate the pressure of point 1 and point 2. So when we're doing problems like this, we have this, let's say this cup. That's just, our second point is 3.75 inches down. Converting that to meters, it's going to be 0.09 meters. We have gravity is meters, density of water is the same, and then our ATM, our atmospheric pressure, is going to be 101.32 kPa. So, we normally look at this derived equation. It doesn't matter how we get to this. What matters is that this equation turns into pressure is equal to atmospheric pressure plus rho g h. So from here, we know that because this is our reference point, that at point 1, z is going to equal 0. So pressure 1 is just, well, pressure 1, when we look at it, it's going to be this. Our height is going to be 0, so this goes to 0. So pressure 1 is just going to be atmospheric pressure, whatever that is, or whatever elevation you are. So pressure 2 is going to be atmospheric pressure plus rho g h, h2, which ends up being 0.09 meters times 9.81 meters times 908 kilograms. I'm sorry, 9.8 meters per second squared, and then 998 kilograms per meters cubed. I just want to show you how this turns into pressure. So this turns into 101.13 kilograms per meter second squared. This right here are the units of 1 Pascal. Right, so we have 101.13 pascals, and most of the time we want to see in kilopascals. So when we convert that, just dividing by 1,000, we get 0.88 kilopascals. So to find the absolute value, it is just going to be pressure 2 is equal to 101.35 kilopascals plus 0.8 kilopascals So pressure 2 is equal to 123 kilopascals. You're literally just adding. So that is how you find the pressure inside a tank. So we're going to introduce a manometer problem. There are plenty of YouTube videos to explain what a manometer is and what it does. I really don't want to make this video too long. Again, it's just example problems, so you could definitely search them up. Basically, they're just a way to show you what the pressure is. We want to find out which fluid would be more efficient to use or more practical to use inside a manometer to give us a reading. PG equals 65 kilopascals. So what height water would give us, what height mercury will give us, and we want to figure out which one we would use. So we want to introduce this equation. Gauge pressure is equal to rho GH. So let's start off with water. So we'd set gauge pressure, so 65 kPa is equal to 998 kilograms per meter cubed. Then we're going to multiply in our gravity. And then our height of water in our column. And we're all going to divide this by 1,000 at the end because we want kilopascals. So, we want to keep everything in kilopascal exactly because this is going to give us pascals. So our height is going to give us, this is just simple algebra, 6.64 meters. That is pretty long, pretty high. Let's use instead some mercury. So we're going to use this density instead. It's much more dense. Again, multiply that by gravity. Height of our little column of mercury. And our mercury height is going to be 0.49 meters. So basically saying, if we were to fill up some manometer with some fluid to tell us that the pressure inside our vessel is 65 kilopascals, if we used water, we would need a column that's 6.64 meters long. That is huge. I'm pretty sure you wouldn't want that in your room. Mercury, on the other hand, you only need 0.49 meters to tell you what the pressure is. So, yeah, you probably want to use mercury. Only downside is, I guess, you can't drink mercury, so, if you want to drink your fluid afterwards, you might want to use water instead. So our next problem, we're going to try to find out what our absolute pressure is inside this vessel using just the height of our manometer. Now this manometer, for some strange reason, has we're assuming perfect conditions for liquid bromine. So this is the density of bromine. Liquid bromine is in this tube right here. And it got up to a height of 1.5, right? So what we're going to do, we need to remember our equation. Absolute pressure is equal to atmospheric pressure plus gauge pressure. So we know that gauge pressure is equal to rho GH. So we have our density. We're going to multiply that by our gravity value. Again, sorry if I'm simplifying this a lot. I just really want to show every step. So our gauge pressure is going to be 45.6 kPa. So our absolute pressure is going to be 98 plus 45.6. So our absolute pressure is going to be 143.6 kPa. So yeah, if you can definitely tell that this is definitely pressurized. So that's pretty cool. Okay, so for this problem, we're going to introduce the idea of specific gravity. So we have this pipe, and it's flowing some gas up, and when we set up our manometer to it, some fluid inside the manometer, we can say it's oil, with the specific gravity of 0.88, it got up to 0.88 meters. So we need a density, and from a specific gravity, how we find the density is that all we have to do is just multiply the specific gravity by the density of water. So in this case, we want our units probably to be in kilograms per meters cubed. So what we would need to do is simply do 0.88 times 1,000 kilograms per meter cubed. And that would give us the density of our oil equal to 180 kilograms per meters cubed. So now to find the absolute pressure, because remember we want to find out what the pressure inside this is from our little manometer, all we need to do is use our equation. Absolute pressure is equal to atmospheric pressure, which is 100 kPa plus rho GH. Our H in this case is 0.88. Gravity is going to be 9.1. Again, we know the units. I'm not going to keep writing them in. We will have to divide by 1,000 to get to our kPa. So we're going to get our absolute pressure to be 100 kPa plus 7.6 kPa. So that would mean that the stream is just not very pressurized. It is pressurized, but it's very weak. So our absolute pressure is going to be 107.6 kPa. Cool. So for next problem, we're going to need to kind of, and I apologize for these drawings. I kind of got tired from doing all the nice drawings on my thumbnail, so really not going to try on the actual video. You guys get the point. You can refer back if you want a nice pretty picture. But so for this problem right here, we have a manometer, kind of double manometer. I don't really know what this would be called, to be honest. If anyone can tell me that in the description, that'd be great. So this top column right here is filled with, I don't know, oil. And then this right here, the rest of it is just water. So what we want to do is find out our height 3 and height 2 if we are only given a ratio between height 3 and height 2. So this means that height 3 is 3 times bigger than height 2. This is not drawn to scale, I apologize. And our height 1 is 0.6 meters. Density of water and oil are given. So what this problem does, I like it, is kind of it integrates what we went over in the first section, talking about the idea that pressure is across. You got to think of pressure as a cross section, right? So if we split this up both ways, we split this up in half, we know that the pressure at point 1 has to be equal from this side and from this side as well, which is great because we can set up 2 equations. Pressure 1, right? This little dot right here is equal to atmospheric pressure, and if we go down from here, remember we add as we go down, it's going to be our atmospheric pressure plus our density of water, gravity, and height 1. Pressure 1 is also equal to atmospheric pressure, and then it's going to also, as we go down, it's going to be equal to our density of oil, gravity, our third height, plus our second height and the density of water. So if we put those in together, what do we get? We can cancel out these terms. We can also cancel out all the gravity terms on each side. So we're going to get this left. So it's just the densities of water and the density of oil, and then all 3 heights. And then again, we're given that ratio. So now what we can do, we can actually divide our densities of water over to the other side and just get our height 1 because we know that value. And then we know that because we've divided, we just have our third height plus H2 because this gets canceled out as well. And now we can actually start plugging stuff in. So we know that, yes, height 1 is equal to 3 times rho oil over rho of water, height 2. So what we just did right here is that we know that H3 is equal to 3 times H2. So we just plugged it in. And now finally, we get this. We just divide. And our second height is going to be 0.18 meters. And our third height, which is just, we just grab this number, right? And we multiply it by 3. So 0.54 meters. So yeah, kind of a cool problem. You can figure out a lot of information again, but you have to remember about your pressure, kind of in a cross section. Awesome. For this next problem, we want to know how much gauge pressure is needed for a hydraulic lift to lift a, I don't know, a 1999 Corbin Sparrow. So we know that the mass of a Corbin Sparrow, obviously, is 610 kilograms, right? Now, with problems like this where they only give you the side view, you have to make sure you know whether the hydraulic lift is a square or circle. We're going to go with the circle in this case. We know that the area would be pi r squared. So I want to introduce this equation as well. So gauge pressure is equal to weight over area. So what are the forces acting right now? We have atmospheric pressure acting down and the weight of the car, which is just mass times gravity, both acting down on that lift. And we want to know how much gauge pressure we need to overcome those forces and actually lift the car. So pretty simple. We just have to calculate this by gravity. We just get 5,984.1 newtons. And then our area, just plug and chug, and you'd get 0.2 meters squared. So our gauge pressure should be 29.9 kPa. Pretty simple problem. For next one, we're going to utilize Pascal's law, what I've been talking about, the fact that you have to, think of pressure as some like infinite cross section. If you make changes over here, those same changes will be felt over here. That's basically the simplified version of it. So we want to know how much oil has to be added in order to lift a crate filled with 160,336 copies of Star Wars Episode 3, weighing 500 kilograms. So we want to know how much we need to fill this column up with oil. So again, we know that our gauge pressure is weight over area. We can calculate that pretty easily. 4,900 newtons over 0.5 meters squared. So that's going to be 9.75 kilopascals. We know that our gauge pressure is rho GH. So this is where we actually integrate these two ideas. So now we obviously know, just, simple algebra, we could rework the equation to give us height. So it's going to be 9.7 kPa over 800 kilograms per meters cubed over times 9.81 meters per second squared. And that's going to give us 1.24 meters. Sweet. All right, for this next problem, I apologize. We're going to be using a lot of freedom units. So a lot of feets and a lot of PSIs, so I think it's good practice though to go over that. So we have some pressure right here. This little bulb right here is filled with chlorine gas, and that also is filled with chlorine gas. This is all assuming that none of this reacts, there's no reactions. The manometer is then filled with some quantity of mercury. Then it's followed by some air. Then it's followed by some amount of water. So we want to know from these certain heights what the pressure in this bulb is. So how we really do this is really going back to that first section when I said if you go down, you add, and if you go up, you subtract in hydrostatics. So you start off at pressure 1, and you go down. So you do not count gases in your calculation. You only worry about liquids. So this is going up. Really, the rule is that the majority of it is going up, then it would be negative. So we can set up pressure 1 minus the density of mercury times gravity times the height of mercury. So we can skip the air because that doesn't matter. And again, we're going to be having a value of a height of water that is going up. So we're going to again subtract by the density of water times the height of water times gravity. And all this, because this is open, this is all going to be equal to atmospheric pressure. So from here, we're just cleaning up the work, moving everything to one side, getting some positive values. So pressure 1 is equal to atmospheric pressure plus gravity plus rho hg, height hg, plus rho water, height water. And I'm very sorry if this seems like kind of overdoing it with the work, but I really want to show you guys every single step. So gravity, again, you just have to find what value it is when it's in feet. That's 32.2. And then we're going to have 848.6 pounds feet cubed. We're probably going to run out of room. Times 8.3 feet plus, so let's run that on this side. I apologize. 64.4 pounds per feet cubed, and times 2.08 feet. So after multiplying that, I already have most of these values already multiplied out. We're going to have 226,992.9 pounds per feet second squared. And we have a little conversion here. In 1 pound force, there are 32.2 pound meters per feet over squared over second squared. And then our final step, I'm sorry that this is so crazy. We want feet squared over 1 foot squared. There's 144 inches squared. Because remember, our goal is to get it in pounds per square inch. So our pressure 1 is going to approximately equal to 18.82 psi. That's how you get it. For a second problem, sorry, my pages are getting a little whack. We have some lake water on one bulb and some seawater on another one, surrounded by oil and mercury. So in this case, there's no gases, so we are going to be accounting for every single height. So again, starting from one pressure right here, pressure 1 plus, so we're going down, so we're going to add the lake water. We're going up, we're going to be subtracting by the mercury. The majority is going up again, so we're going to subtract by the oil. And then the majority is going down, so we can add our seawater. And all this is going to be equal to pressure 2. So really the equation that you really have to remember is just our pressure 1, if you ever see a system like this, is really the delta rho GHs is equal to P2. And in the previous problem, it's going to be the same thing. That's rho GH is equal to PATM. If you can remember these equations, you'll be set on the exam. So in this case, we're finding out what the pressure difference is between 1 and 2. So what we can do is just move over pressure 2, subtract it over. So we have pressure 1 minus pressure 2. That means this is going to give us how more or how less pressure 1, or bulb in the pressure 1 is compared to pressure 2. So we still don't know. So minus lake water plus mercury, oil, and then seawater. And then what we can do is we can substitute out the gravity. Oh, I apologize. There's a gravity right there. It's pretty bad. And now we have our mercury.
oil, seawater, and our lake water. So after doing all these calculations, you get 22,935.8 pascals. We want it in kilopascals. So I'm going to get 22.93 kilopascals. So pressure one is 22.93 kilopascals more or higher than pressure 2. Alright, we're kind of running out of time. Not really that there's a time limit, but this video is getting super long, so I'm just going to quickly go over, not even add any numbers to this, how we would solve something like this. Again, because they're horizontal to each other, again, we can do the P is equal to rho GH equal to pressure 2. So in that case, we would go down. So we would add the water, however much the height 1 and height 2 are. So it would be height 1 plus height 2, right? Because we go down. Sorry about my drawing skills, this is really bad. But again, I have to kind of quickly go through these. The oil is just height 2, because it's just up to here, from this line to this line. And then water would, the rest of the water, because it's going up. This was going up as well, so the oil, that's why it was subtracted. The water, again, is going up, so it's subtracted, and that is just height 1. So we would set that equal to P2, and you would just solve that. For this next one, if we want to solve how much height we would need here, all we would have to do is gauge pressure, we would go down. We can set this as like kind of a baseline right here, because we know that the pressure here has to be equal to the pressure here. So if we go down, we would add this rho H1, and then we would go back up, subtract the rho GH3, and set that equal to our atmospheric pressure because it's open. This goes to 0 because we're talking gauge pressure. And then we can isolate stuff, and we know that H1 is 2 meters. So that's how we would solve for our height. We would just move everything to the side, our height 3. If we wanted to know pressure 1, all the way down here, it would simply be pressure 1 is equal to gauge pressure plus rho G down here. So H1 plus H2. Yep, pretty simple. Okay, so this final one, we're going to be introducing a little bit of trig. Basically would work the same. If we start from pressure 1, right? This is pressure 1. We'd go down. So pressure 1, we would add that water, whatever that water is. This height is A, so that's our height. Then we would again, because it's going down, this is mercury, so we would add our mercury. This is 2A in this case, from this line. Sorry, I really did do a really crappy job at drawing this. So from here to here, it's 2A, that's that height. And then we would go up. Because we're going up, we're going to subtract that last A value. Pressure to 2. These guys are exactly the same, cancel out. We're finding, they give us a value, pressure 2 minus pressure 1 is equal to 20 kilonewtons per meters squared, kilopascal basically. So we can do P2 minus P1 is equal to 2 rho Hg, gravity times A, and plug things in. This is literally just substitute things in. We get this. So now we know what our A value is. We want to find our theta. We can set up a little triangle right here. We know that this angle on this side is going to have to be equal to this angle. This is just geometry. So we'll assign that as a value of theta. We know that this height right here is 2A, and this height is 0.3. That's our hypotenuse. And we're finding for theta. So set up SOHCAHTOA. I still use it to this day. So we know that opposite is 2A, and our hypotenuse. So we want to use sine. Sine of theta is equal to 2a over 0.3. We use arc sine to get it on the other side, whatever that would equal. I think it would be, because we know what a equals now, multiply that by 2. So it's just 0.5. So yeah, our theta will be equal to 30. Boom. That was a horrible theta. Let me fix that. Awesome, guys. I hope you found this video kind of helpful, at least. So if you definitely find a mistake, please let me know in the comments so I can fix it. I will be more than happy to re-upload a video. I'm not perfect. I make mistakes. If I do have something that I have said that is wrong, again, I don't have a doctorate in this stuff, so I'm not the best source to learn hydrostatics. But anyway, I hope these example problems helped, and good luck studying, everyone.